Lastly, we're gonna speak, after the summary, we're gonna speak lastly about an alternative to the hybrid pi model that we've been using in our analysis, that is called the H parameter. And for that, we refer to the notes on H parameter, first of all, alone, which are taken from Fluid textbook, and this is a textbook that the higher certificate people use in electronics 1. But we share this note with you to introduce the concept of hybrid parameters, or H parameters basically. So considering a linear circuit, of which the transistor is normally not a linear circuit, because we go from VBE to get the IC, which are related by an exponential function. But we ended up linearizing it, if you recall properly. We ended up having a linear equation between the input and the output. All the different gains we've been getting are actually linear equations, because when you say V out is equal to some gain, which is like a constant, times the input voltage, that means they can be represented by a line of which the slope is the gain. Agree? So that's a linear relationship. So H parameters are applicable to any linear circuits in which you've got, on the input side, you've got a certain voltage V1 as well as a current I1 going into the linear circuit. On the output side, you've got V2 and an output current I2 going into the linear circuit. That's the type of systems to which H parameters are applicable, of which a BJT amplifier circuit happens to be one of them. Already you can pick up some similarity. So your V1 will be your VI, if you pick up some similarity. II will be IB if you're in common emitter mode, or if you're in common collector mode, because the input is on the base. And I2 would be IC if you are in common emitter, and considering the direction as well. If you're in common base, for instance, the output is on the collector, but the input is on the emitter. So the I1 would be IE, while IC will be minus I2. So I2 will be minus IC, because now suddenly IC and IE have the same direction. So since I1 and I2 have got opposite direction, so if I1 represents IE, here I'm talking common base, then I2 will have to be minus IC, because naturally IE and IC have got the same direction. So now if we take I2 in the opposite direction to I1 being IE, then I2 is definitely minus IC. So we can see that all the three configurations are responding to this model. So now with this model, which is not only used in electronics, it has been proven that V1 is equal to H11. It goes from the consideration that V1 is equal to H11 I1 plus H12 V2, and I2 is equal to H21 I1 plus H22 V2. So this is the guiding equations of the linear circuit when it comes to hybrid parameters. So that means you can define a linear circuit which has got such a voltage and such voltages and currents. You could define it by a matrix H11, H12, a matrix of parameters, H121, H22. So that's enough to describe the behavior of the linear circuit, and that's the approach that H parameters use. So now, it's very important for us to understand H parameters, because some questions might be given in terms of H parameters. But since we've studied hybrid parameters and both lead to the same answer, we just have to bring them close to each other in order to establish the conversion, how to convert from one mode to the other. That's the one thing. And the second thing will also be, how are the H parameters H11, H12, H22, and H21 and H22, of course, named when it comes to BJT amplifiers? What are their terminologies, and what are their terminologies in different configuration modes? But to start, let's start by establishing the relationship between them. in order to convert from possibly given h parameters towards hybrid pi that you are familiar with, this is the process. The process normally goes as follows. You would normally have your h11 parameter to be your r in, your h12 will be 0, and 1 over h22 will be equal to r out, and which means that h22 is actually your output, the inverse of your output impedance, and your h21 is actually equal to beta. For instance, how can we prove that h21 is equal to beta? That is demonstrated by redrawing the h parameter AC equivalent circuit of a BJT amplifier as follows. You find that in the notes, and if you make analogy, you will see that the current I2 being H12 plus times I1 will result in beta then being H21, sorry. There is a mistake. This is supposed to be H21. This is H21, okay? So I1 being IB, then that will mean that beta is actually H21. H21 is actually beta, and that's demonstrated in the notes as well. Very important. So whenever you're given a problem with h parameters, you just have to take the h parameters you are given and say h12 is 0, h11 that you given, that's your r in basically. From h22, work out its inverse, and that will be your output impedance. For h22, and the h21 will be your beta value, and then you can work in hybrid pi mode, which is what we've been doing. I think it's important for me to also then, because you need to know which one. Normally they will not tell you h11, h122, because those are generic h parameters that are applicable to any linear circuit with those characteristics. In the specific case of BJT amplifiers, when it comes to h parameters, there is a very important table that shows in each configuration mode what name do we use for h parameters. This is the table I'm referring to. So if you are in a common emitter notation, h11 refers to HIE, h12 is what we call HRE, h21 is HFE, and h22 is HOE. So as you'll notice, all the h11 parameters are HIs, because they're on the input basically, and the letter that follows I is normally representing which mode we are in. So for instance, common base, it will be HIB for h11. So when you see HR on the other side, that represents h12, and that's often 0 as we said. And h21 will normally be your HF. So in common base, that will be HFB. In common emitter, that will be HFE. In common collector, that will be HFC. And similarly for common collector, for H22, which is HO, followed by the letter representing the type of configuration in which you are. So you just have to convert, given HRE, HFE, and HIE, for instance, in the case of common emitter, you should know that HIE, which is H11, will represent your R in. HRE will be equal to 0 because it's H12. HFE is your beta, and HOE, 1 over HOE will give you your output impedance, and you can work out from there. So now, when you say output impedance, actually we're referring to the entire amplifier. But in reality, if you limit it to the small signal of a transistor in a common emitter situation, for instance, so we actually referring to RO, basically for 1 over HOE, and R pi, not R in anymore, but R pi only, if you're looking at the transistor alone, not the amplifier as a whole. So R pi will be your H11, which will be HIE. Your HRE, of course, is H12, which is 0, but also HFE is your beta. HFE is your beta, right? IB, okay. So, and that's what we're referring to. So, normally we say R in, R out, but no, in actual fact, it's R pi for R in, depending on which transistor mode which configuration mode you are in. But in the case of common emitter, for instance, when we said R in, that's the R pi actually, that's HIE. Okay.